Okay, today we're going to kind of continue with what we've been talking about and working with the greatest common factor to help us simplify some fractions, including monomial fractions. So here's a problem to start with. One of the Czech Republic's royal coronation jewels is the St. Wenceslas crown. It was made around 1345 and is decorated with 44 spinels, 30 emeralds, 22 pearls, 19 sapphires, and 1 ruby. Write the fraction of jewels in the crown that are emeralds in simplest form. So when we're writing a fraction, what are the two parts of a fraction that we need to know about? Right? So we have a part being compared to the whole. And in this case, the part that we are interested in are the emeralds, and we're going to compare it to all jewels. So we have to find out the total number of jewels. Okay. So writing the fraction of jewels in the crown that are emeralds and then simplify. So we have the number of emeralds to the total number of jewels in the crown. So 30 over 116. And method 1 will use the GCF of 30 and 116. So we first find the greatest common factor. You could use the upside down cake. All right, so let's do that to remind you on how to do that. We look for numbers that divide into both. So they're both even, they're divisible by 2. 30 is divisible by 3, but 116 is not. 30 is not divisible by 4. 116 is not divisible by 5, not 6. We could try 7. Well, let's just start with 2. So 30 divided by 2 is 15. And then 116, when I do this, I take the 2 kind of like a partial, like the short division. 2 into 11 is 5 with the remainder of 1. And then 2 into 16, which is 8. So if I just don't happen to know what that other factor is. Then I compare 15 and 58. Not divisible by 2 or 3 or 4. Both not divisible by 5 or 6 or 7. All right, I'm pretty sure that this is it. So at the bottom here, right here, this relatively prime numbers that you have are already in numerator / denominator form. So it said in this method we're going to find the GCF, and then we're going to divide top and bottom by that. By finding the GCF using this form, you kind of have already found that simplified fraction. So let's double check that we're... So they're finding that the greatest common factor is 2. We already found that. If you divide top and bottom by 2, you get 15 over 58. Okay? So using that ladder method, when we get the 2 numbers at the bottom that are relatively prime, if we put them in order of numerator then denominator, we have our simplified fraction. The other method would be use of prime factorization. So if we write out the prime factorizations with no exponents, then we can cancel out any factors that are the same on top and bottom because they equal fractions equal to 1. So common factors, so that 2 over 2 is a fancy form of 1. It's equal to 1. Then what you have left, you multiply. 3 times 15 and 2 times 29, you get the same thing. So again, the fraction of jewels that are emeralds is 15 out of 58. Use the information from example 1 to write a fraction of jewels in the crown that are the given jewels, simplify if possible. So first we're going to do the pearls, and then we're going to do some of the others. So if we recall from the original problem, there were 22 pearls. So let's write that fraction 22 pearls out of the 116 total. And then we could use the upside down cake as my way of liking it. Oh, well, let's just make sure that we don't change the number on us. So if we divide by, say, 2, how about 11 and 58? Are they relatively prime? My guess is that the answer will be 11 out of 58. And there they are. Let's try another one. Sapphires. If you recall, there were 19 sapphires. 19 sapphires out of 116. 19 is a prime number. Its only factors are 1 and 19. So we have to see if 19 goes into 116. So try that out. The fraction of sapphires is 19 out of 116 because 19 was prime and 19 is not a factor of 116. The two numbers are relatively prime and simplified already. How about spinels? If you recall, the number of spinels was 44. So our fraction is 44 over 116. So putting it in this form and using the GCF, oh, look at that. And if I would have thought about it, we could have started with 4 because 44 is divisible by 4, and so is the last two digits of this number. Therefore, we could have started with 4, but I didn't. So here is our simplified fraction, 11 over 29. All right, here's the next example. Example 2. What about simplifying monomial expressions? You have two methods that you can use. One, we can use the cake or the ladder, just like we did, and then divide out the GCF, or if you're putting it in the form of the ladder, the last two digits will be the simplified form. So you could totally do that. You could start out with 6x squared and 12xy. Factor out GCF of the numbers. We could try 6 and get x squared and 2xy. Then look and see, oh look, there's 1x here, 2 here. One of them could be factored out, which would leave 1 behind and 2y, and since these are relatively prime, this becomes our fraction, x over 2y. Or we can write this out as a product of its prime number. Do the prime factorization. Since the factor tree for 6 would be 2 times 3, you could write times x times x. For 12, it's 2 times 6, so there's just one more 2 there, like a 4 times 3 times x times y, and then come back out and factor or cancel off. Here's a fraction equal to 1. Here's a fraction equal to 1. Oh, I totally bypassed the 3. There's a fraction equal to 1. So what do you have left? 1 times 1 times 1 times x. 1 times 2 times 1 times 1 times y, so 2y. Either way, your answer in simplified form is x over 2y. This other one has negative 4x cubed. Okay, so in this case we have, since the whole thing is going to be a negative fraction, I'm not really concerned where you put the negative. Okay, in most fractions we just put it like right there and put the fraction bar to the side of it. Then we can factor out 2 times x times x times x, and here we just have 2 times x. So that when we cancel out fractions equal to 1, we'll end up with a negative 1 times 2 times x, we can put that back into 2x squared, and then it's over 1 times 1. So do we need to put the denominator in this case when they simplify out to 1? We don't. So a negative 2x squared becomes a simplified form. If you put it all over 1, it would not be counted wrong.
Or all over x.
I'm going to also do the ladder method. In this case, we're going to leave, so we'll have 4x cubed and 2x. I'm going to just factor out the GCF, which is, so it's a negative 4x. So what we're going to have is a factor of 2, so we'll get negative 2x cubed and an x left over here. We can do 1 factor of x, so negative 2x squared, and since this is equal to 1, x divided by x is equal to 1, your fraction looks just like the way we got the answer before, and remember there's no need to write the denominator of 1, but if you do, it won't be wrong. So how about you try it? This will be your turn to try. Okay, for this one, sure is a lot easier having to do those prime factorizations or factoring the monomials when the number part, the coefficient, is already prime. So 2 times x times x times x times y over negative 3 times x times y times z. I'll change colors here, and then I'll cancel out factors equal to 1. Only one of the x's cancel out, and then the other is the y that cancels out. So what we're left with is 2 times x, 2x squared, over a negative 3z. I'll also show you the other method. So if we line these up, numerator first, denominator second, factor out, since I can't, it's pointless to factor out a 1, so I'll go ahead and factor out my x, and I'll get 2x squared y, negative 3 y z, factor out my y, 2x squared, negative 3 z, and they're relatively prime, no more common factors. We have the final answer.